So basically, you always use the upper two bits in this case because you have 4 pages only to identify the virtual page the byte resides in, and the remainder will be the offset from which you're starting. So if you have 8 pages, for example, if you had a virtual address space with 8 pages instead of 4, you would use the first 3 bits for your address needs, and then the remaining will be your offset. Okay, so now you can basically know that, well, you need the 5th element in the first page by looking at VPN and offset together. So now you simply need to map the VPN to a physical page number PPN, also called a physical frame number. So which physical page can we find our byte at address 21 again? It's basically page frame 7. And what is 7 in binary? Okay, so the 7 in binary is basically 3 ones, right? So it's the PFN is 3 ones. It's basically because it's like the first. So if you look at so if you look at the PFN value here, the first one is 1, the second one is 2, and the third one is 4. 4 plus 2 plus 1, which is equal to 7. So you have an address translation, virtual address translation unit that basically takes your 0, 1 and basically in reality translates it to 3 ones. Basically the physical address space name, the PFN. Okay, so the offset will stay the same because the offset just tells us which byte within the page, within the physical address, this element is. Okay, so the physical address becomes basically 3 ones, 0, 1, 0, 1, and this is exactly where we want our load to fetch data from. So with this basic overview in mind, we can now ask a few basic questions you might have about paging. Where are these page tables stored? That's 1. What are the typical contents of the page table and how big are the tables? 3. Does paging make the system slower or faster? Okay, so let us in the beginning imagine a 32-bit address space with 4,000 pages. Both virtual and physical have the same number of pages, so I mean it's even very simple. You might need a calculator to quickly get this, but how many bits do you need for the virtual page number and offset? You're right, it's 20 bits for the VPN and 12 bits for the offset. That is actually 32 bits, out of which you're actually using 20 whole bits for the VPN and 12 bits for the offset. Okay, so 4 KB is 2 to the power 12, and your number of pages is basically 2 to the power of 20. So a 20-bit VPN implies that there are 2 to the power of 20 translations that the OS would have to manage for each process. That is roughly a million translations, basically. So if your page size is 4 KBs, you need is 4 KBs, and you have 32-bit memory. Okay, you have 32-bit address space. You have a million pages to translate. Okay. What does this mean? That means that you need 4 megabytes of memory needed for each page table. So, because since basically, as we said, the virtual, you have the page tables per process, right? So now, for each process, you'll have this translation. And since for each process you have this translation, that means that you will have the 4 megabytes of memory for each process. And that is pretty large, because if you have 100 processes running, this means that the operating system would need to manage 400 megabytes of memory just for page translations. Even now, with large memories, that's half a gig of memory just to do the page translation. Okay. So what is a page? What is in a page table? The page table is data structure, as we said. So anything will do. The simplest implementation of a page table is called a linear page table, which is just an array, and the operating system indexes the array by the virtual page numbers basically, and looks up the page table entry at that index in order to find the desired physical frame number. So you basically have a simple linear structure where you have a one-to-one mapping between the VPN, the virtual page number, and the PFN.